Okay. Let's start with the record. Okay, good morning, everyone. This morning we are a bit less than usual, but maybe some people still need to connect. So, or maybe people are already on holiday since we have a long weekend ahead. I want to share with you, first of all, this one, the calendar. So today we are going to do lecture 16. Then Monday is going to be holiday. And then next week we are going to do lecture 17 and 18. What I want to point out is that midterm 2 is going to be on lecture 10 to 15. So up to the topic that we covered last time. So from the cover that we are covering today on, this is going to be the material of the midterm 3. Okay. So this lecture was about period frequency, angular frequency, so essentially uniform circular motion. So I want to share with you different slides that I prepared. Okay, share. Okay, so let's see if I give you a different point of view, if it can help. I want to, sorry, I have my face really in the middle, and I don't want that. Okay, so this is about the circular motion. So essentially you have an object that is moving around. Oh, if I do like this, I cannot see the pointer. So excuse me, but I have to keep it this way. I hope you still see it big. So a circular motion, you have a point at a certain distance from the center that is rotating around the center. Okay, what you see is that R is constant and is the radius. The velocity, you know that the velocity is a vector. So here the intensity is constant. So the speed, which is the magnitude of this vector, is constant, but the velocity is changing the direction every second, constantly. So here, instead of having everything as a function of R and as a function of V, the easiest way is instead to define an angular position. So an angle theta, and this angle theta from trigonometry, we can say that if is essentially can be defined as S divided by R, because we know that when sin theta over theta for very small angles is like sin theta can be approximated with theta for very small angles. So that's why we come with theta equal to S divided by R. And so if we have this, we have that essentially we can define the position not only with R, a vector, but also with the angle. So this angle will be in between 0 and 2 pi. And normally what we want, we define it radians. So radians, I put here the value of it. So 1 radian is equal to 180 degrees divided by pi. So is equal to 57.296 degrees. And so the degree measure of the angle, 1 degree is pi divided by 180 degree radiant, which is 1 degree is 0.017 radiant. Okay, so you're going to use these values sometimes because you have radiant and he asks you the degrees, or vice versa. You have degrees and he's asking, the problem is asking for you to find radians. So then what is very important to notice is the period. The period is called like the time required for one complete rotation. So if you start from here, how long it takes for you to arrive again to the same initial position. So the velocity you can define with this, the velocity vector V, which is going to be equal to 2 pi R, which is our circumference, divided by the period. So this is the displacement, if you want, in an entire cycle. You do one circumference divided by the period T, which is the time required for one complete rotation. This gives you the velocity. And the velocity, as I said before, remains constant in magnitude, but it constantly changes its direction. Okay, and you see here this vector pointing all over the places. Then we also have an angular velocity. The angular velocity, remember when we defined the velocity, was displacement divided by time. So final position minus initial position divided by the time that you needed to do that displacement. Now here for the angular velocity is exactly the same, but here instead of the position, the usual position that you would have, you have the angular position. So our angle, so you have delta theta with theta final minus theta initial divided by delta t. So for example, here in this is the example, this is initial, this is final, this is delta theta, and you go from one T1 to T final, which is T1 plus delta T. This defines your omega. And this omega is not a vector. So it's easier to use because it's not a vector, because this is a scalar quantity and this is a scalar quantity. So another unit that is used is revolution per minute. Sometimes you find revolution per minute. 1 revolution per minute means that you do 2 pi radians in 1 minute. So 2 pi radians divided by 60 seconds gives you 0.10472 radians per second. Okay, so it's just 1 revolution per minute is essentially 0.110472 radians per second.
Hey, Veronica, could I jump in for a sec?
Yes.
Okay. First of all, I do want to add, yes, RPMs, we put that, and a textbook uses that in a lot of problems. So being able to convert between that and radians per second is important. In the chat, Yuna is asking a number of questions about why delta theta isn't 0 when the object completes one full circle and comes back around. So Yuna, delta theta is going to keep on increasing as an object goes around and around and around. So delta theta will become 360, 720, 1080, right? You've been watching the Olympics, you know how to add 360 really fast over and over, okay? Or if the object is going in the clockwise direction, then delta theta increases in the negative direction, okay? So it doesn't reset to 0 when an object completes one revolution. It just keeps on increasing. And similarly, if we ask what is the path length displacement of an object, that path length keeps increasing over time as well. Okay, we're going to call that usually delta S, right? Okay.
Yeah.
I hope that helps explain. Sure.
Yeah. So here again is conventional to treat theta and omega as a quantities that have a sign. So normally the sign is positive for counterclockwise rotation. So like you would go with trigonometry, essentially is following the same trigonometry idea. So it goes in this way, it increases in this way, and is negative for a clockwise rotation, okay? So yeah, if it says negative theta, you know that you move from this position down here, okay?
This is also the convention we use in trig class, right?
Yes, the
So
same
trigonometry class.
Yes.
Yeah, exactly, right? Positive theta increases this way, negative theta that way. And we're going to use the same sign convention for all rotational quantities, like torque, for example.
Yes. And so let's see immediately one example. For example, we have a 4 centimeter diameter crankshaft that turns at 2,400 RPM. What is the speed of a point on the surface of the crankshaft? So we have 204,000 revolution per minute. So divided by 1 minute. If we want to bring to revolution per second, I have to multiply 1 minute, divide by 60 seconds, 1 minute and 1 minute goes away. And then I found 40 revolution per second. Okay. If I want to find the period, because to find the speed, I need to find, right, the distance, the displacement, which is 2 pi r, divided by the period. So the period, it takes for one revolution, it takes 40 revolutions per second. So the period is 0.025 seconds. It takes 0.025 seconds to perform an entire revolution. And then the velocity is 2 pi r divided by t. So 2 pi r, it says here that is 4 centimeter diameter. So we know that the radius is half of it. And this is centimeter. We need to bring it in meter. So that's why this zeros in front of it. So 2 pi multiplying 0.020 meter divided by the period that we just found, it gives you 5.03 meter per second. Is it meter per second? Yes, 2 pi doesn't have any dimension. And then we have meters here and second here. So this is a velocity and it works really fine. We also have a different alternative method, which is omega is equal to 2,400 revolution over 1 minute. So I want to bring everything, I want to find omega, which is in radians per second. So I have to multiply by 1 minute divided by seconds. So I have the seconds. And then I want to say 2 pi radians is 1 revolution. So if I do that, I'm able to remove revolutions from here. I'm able to remove minutes from there. And what I have is radian per seconds, right? So I have an omega angular velocity of 80 pi radians per second. The velocity, again, is omega r. And is, so we just multiply the omega that we find for the radius. This is an alternative method. So you had 2 methods to do that. Okay. Then, and this is an equation. I don't know if it was explained here, perhaps not, but it was in Mike's slides. This is another way to identify the velocity as a function of the angular velocity. Then what we have, we might have an acceleration. So if we have an acceleration, the acceleration is in circular motion is called centripetal acceleration. So an object moving at a constant speed in a circle must have a force acting on it. Otherwise, it will move on a straight line. And indeed, you see if you, for example, if you and your friend take your hands and you start to move it in a circle and go in a circle, what will happen is if you open your hands, you stop going in a circle, right? So to keep the circle, you need to have a force acting on it. Otherwise, you would just move in a straight line. And so here is the same. So we see this is the radius, this is the velocity, and this the acceleration, because you have to have a force pulling in this way. And it's a constant acceleration toward the center of the circle. And it's called centripetal acceleration, as is defined as v to the square divided by r. Okay, this is how it's defined. And so here we see, if we want to put the force, we have that a force is along this acceleration, because we know that force is mass time acceleration, and it goes in the same direction of the acceleration, so towards the center of the circle. And here we have a velocity, which can also be called tangential velocity, because you see it's always tangent to the circle in that point. And is 2 pi r divided by t. So the velocity that we defined before is this, we can call it velocity, but it's also called tangential velocity because it's tangential. While the acceleration goes toward the center, and it's called centripetal acceleration, and it's v squared divided by r. Okay, so the centripetal force from the centripetal acceleration is the one required to keep an object of mass m moving in a circle of a radius r, and is m a centripetal force, but we know that the a centripetal force is also v squared divided by r, but we know that v is also equal to omega r. So if we substitute omega r here, we have m omega squared r to the square divided by r, so it comes to m omega squared r. Okay, so for example, here, if I have a ball that is turning, I'm going to have the centripetal force will provide a tension in the string, for example, going toward the center, or sometimes you have the centripetal force is provided by the friction when you are in a car and you are going along a big turn. So let's see now some examples. I think it's easier if you see some examples. Are there questions that we need to address, or we are good?
I think we're pretty good now. Yeah.
Okay.
Yep.
Very good. So let's see with an example that makes it easier for all of us to understand better. So here, for example, we have a 1,200 kilogram car that rounds a corner of radius 45 meters. If the coefficient of friction between the tires and the road is this one, what is the maximum speed the car can have on the curb without skidding? Okay, so here you see the car is like going in a circular motion around the center with the radius r, and you see the velocity is the tangential velocity and so on. Then if we look at the side view, what we see is that we have along the y-axis normal force and weight going exactly one up and the other going down. And then we are able to have the car going around the circular motion thanks to the fact that there is this friction. So here our friction is like our force that we described before, the centripetal force that described it before. So if we look at this, let's look for the y-axis first. We don't have any motion along the y-axis, so the sum of the forces along y is equal to 0 and is equal to the normal force minus the weight. So normal force minus mg, which brings to normal force is equal to mg, the mass of the car, and g is the acceleration, gravity acceleration. So this, we know it from the previous classes. We have done it many times. Now, what is new is instead what we have along x. What we have along x, we have friction, and we know that it's going towards the center. So if we take this as a positive x-axis, then we say mu s normal force, which is the typical friction, is equal to mass acceleration along x. The only new things that we have now, while normally you would stop here with this problem, now we know that is a along x is our centripetal acceleration. So you have to put v squared divided by r. And so if you put this, normal force, we found it before, is mg. So we have the mu s mg is equal to m v squared divided by r. I remove mass because it's everywhere. And now it was asking the maximum speed. So I just found the velocity as the square root of mu s rg. I substitute the values and I found 19.0 meter per second. Okay. And we see that the results does not depend on the weight of the car because the mass essentially goes away. So it depends really on the friction, on the radius, and of course, gravity, which is the same for everyone. Okay. So I don't know if this makes it easier. So essentially it's a problem like the one you have seen until now. The only difference in this case, yes, is the fact that the friction here, the friction force is also our centripetal force. And so we can do this extra step. Okay, so here let's see banked curves. Let's make it a bit more complicated, and let's assume that the car of before, instead of being in a just flat road like this one, let's make it banked, okay? So if the road is banked at the proper angle theta, a car can round the curve without the assistance of friction between the tires and the road and without skidding. What bank angle theta is needed for 900 kilogram car traveling at 20.5 meters per second around the curve of radius 85 meters? So in this case, if we select this and this as axis, we have that the weight, as you now know pretty well, goes always down. Doesn't matter how the surface here is, it just goes down. So you see the weight is perpendicularly down, while the normal force is perpendicular to the inclination of the surface. So if this is our angle theta, the normal force goes up, and angle theta is this one, but is also this one. So here you need really to make attention how to propagate the theta around, because most of the problems comes from the fact that some people just make a mistake and consider this theta instead of this one. Okay. Now, this is the normal force. So you see that the weight is all along y, while the normal force has a component along y and a component along x. So let's see, along y, we have that there is no motion. So the components of the forces are going to be equal to 0. And the components of the forces are n cosinus of theta minus the weight. So n cosinus of theta minus mg equal to 0. Okay. Then along x, instead, what we have, we only have the component of the normal force, n sin theta, which is equal to mass centripetal acceleration, v squared divided by r. So if I do here, what I do. So if I do, let me see. Okay, I bring this in the other side. So I have n cos theta equal to mg. And here I have n sin theta equal to mv squared divided by r. If I do the ratio of n sin theta divided by n cos theta, so I do the ratio between these two, this is equal to tangent of theta, which is equal to, in one side, we just said I have mv squared divided by r, while in the other side, I have only mg. So the mass goes away, and I find that tangent of theta is equal to v squared divided by gr. So theta is equal to the arc tangent of v squared divided by gr. I know the velocity, 20.5 meters per second square. I know g, I know the radius. So as you see here, we were able to not use the mass of the car at all, because the mass of the car is essentially not important. Could be anything because it doesn't depend on it. Okay, so, and we find the value of the angle. Is that fine? Are there questions that we need to address? Okay, so you see that here in this case, you don't need the friction, but it's actually this component of the normal force, which gives the centripetal acceleration. So it's enough to keep the car moving along the curve, the road. Okay, let's see another problem, spinning in a circle. So we have an energetic father that places his 20-kilogram child in a 5-kilogram cart, to which is attached a 2 meters long rope. Okay, so we have, this is the dad, this is the child on the cart, attached to a rope. He then holds the end of the rope and spins the cart and child in a circle, keeping the rope parallel to the ground. If the tension is the rope is 100 Newton, how many revolutions per minute does the cart make? So what we know is the mass of the kid and the cart, that doesn't really matter. Here we just do 20 plus 5. This is just something to distract your attention, but at the end of the day, it's like if you have just a bigger child of 25 kilograms, then you have the radius here, the distance, which is 2 meters. And then you have the tension of the rope, which is 100 Newton. And the tension of the rope goes towards the center and is what is making your centripetal force. And we have to find omega. How many revolutions per minute does the cart make? And we have to find omega in RPM. Okay, in revolutions per minute. So this is again, the pictorial representation. We want to do the physical representation because it's always easier. So we do our kid as a dot, normal force going out, going up, weight going down. It says that the rope is parallel, right? Where is say that? Keeping the rope parallel to the ground. So we don't have any angles. And so we have only this component. If we look at this component along the Z axis or Y axis, whatever you want to call it, we have the normal force minus the weight, which is equal to 0. Here normally is capital N, here is small n, but it's the same, it's the normal force. Minus the weight equal to 0. And here instead, along the x-axis or along R, what we have is T equal to mass time acceleration. We know that this is a centripetal force, so we need to have the centripetal acceleration. So mv squared divided by R. So if I want to find the velocity is equal to the square root of RT divided by M. Do I know R? Yes, it's 2 meters. Do I know T? Yes, it's 100 Newton. The mass is 25 kilograms. So I have everything. Newton, remember how to, is a mass time acceleration, right? So here we have a mass, which remove the kilograms. And then we have acceleration, which is meter per second square. So we have meter square divided by second square. If I do the square root, comes to meter per second. And this is the amount. Okay, now I have the velocity. Is that enough? No, because it's asking revolutions per minute. So I need to find the angular velocity, which is the tangential velocity, 2.83 meter per second divided by R. So if I do that, I found that the dimension is only radian per second, 1.41 radian per second. How do I change from radian per second to revolutions per minute? Is written down here, radian per second. I can multiply for 1 revolution divided by 2 pi. And I can multiply by 60 seconds divided by 1 minute. And I found 13.5 revolution per minute. I have a slow battery. Let me move 1 second.
While you do that,
everything okay? Are there questions?
I'm sorry, Veronica. I don't know if you can go back 1 slide.
Sorry.
I just wanted to point out to everyone that those two diagrams in the previous slide were different points of view, right? It said that, but it was just sort of in small type. This one is a top view looking down from above, whereas that one is a side view looking edge on to the circle of motion. Okay, so in this upper picture, the normal force and the weight would be in and out of the page. So by rotating down into the side view, the normal force and the weight are vertical. Yeah.
Yeah.
That's all. Just an important little
Mm-hmm.
thing to
Are
know.
there questions? So is this clear? Oh. Okay. So if it's clear, I can go on. So you see, at the end of the day, you have to reuse the same equations that you were using so far, but you have to replace A with V squared divided by R. And then sometimes you need to pay attention because it's requested omega. Some other times, like before, it was asking the angle. So yeah, it's a bit, those are the tricky differences that you need to pay attention to. Okay, let's see another problem, another example. In this case, we have a satellite that moves at constant speed in a circular orbit about the center of the Earth and near the surface of the Earth. If the magnitude of its acceleration is 9.81 meters per second square, and the Earth's radius is 6,370 kilometers, find the speed v and the time required for one complete revolution. So this is the planet, this is the satellite, this is the velocity, like the tangential velocity. The acceleration goes toward the center of our planet all the time, right? The centripetal acceleration. So here we have that the centripetal acceleration is v squared divided by r, which is also equal to g, right? Because it's gravity. So v is equal to the square root of rg. So if I substitute the information that I have here, I change this from kilometers to meters. This is the acceleration. I found that this is the velocity in meters per second. Here you change it to miles per hour, but it's fine. You just need to keep meter per second. Doesn't matter, this one. And then the period is going to be 2 pi r divided by v, by the velocity. So you see 2 pi, we know the radius, we divided by the velocity, it gives 5,000 seconds, which is also equal to 84.3 minutes. This is the time required for one complete revolution. So here is not using the forces, it's just using the acceleration, which is equal to g. And yeah, if we were using the forces, saying there is no force along x, but there is only one force along y, you would have get the same results because essentially the mass goes away. So this is another example.
Could I just add one comment? And that is in the next lecture, in lecture 17, when we talk about gravitation, one of the things we're going to point out is the value of little g, or the local value of acceleration due to gravity, decreases as you get farther from the surface of the Earth. So this problem is assuming that we're just skimming the surface of the Earth, right? So that's why little g has a value of 9.8. Otherwise, once you go further up, it's going to drop to 9.7, 9.0, or way out where the moon is, it's much weaker than that.
Yes. So this is a simplified case. Okay, then we can also speak about the centrifuge, which is a laboratory device using chemistry, biology for increase the sedimentation rate and the separation of a sample. by subjecting it to a very high centripetal acceleration. And so what you get is that you have essentially an apparent weight. And we will see this in this example. So here we have a centrifuge that rotates at the rate such that the bottom of a test tube travels at the speed of 89.3 meters per second. The bottom of the test tube is 8.50 centimeters from the axis of rotation. What is the centripetal acceleration at the bottom of the test tube in meters per second and in G, where 1G is 9.81 meters per second square. So what we write is a centripetal acceleration is V square divided by R. So V square, it says that 89.3 meters per second square divided by 0.085 meters, which if we do this calculation brings to 93 and 800 meters per second square. And if we then divide by G, we have 9.56 Gs.
So in recitation, we talked about how 1G can be used as a unit of acceleration, right? Yeah. Instead of meters per second squared, people like to convert things into Gs, especially in the life sciences. This is, or when talking about human physiology. Yeah. So for centrifuges, people love to do this. So there, in the past, we've asked midterm questions with this exact same question. What's going to be the effective number of Gs felt by the contents of the test tube at the bottom of the test tube?
Mm-hmm. Yeah. Okay. And I actually finished a bit earlier because I finished everything. I went so fast. So I don't know if you have, we have 10 minutes for questions. Or if we want to see another problem from the tutorial. We can look at, let's see. We can look at Mike's. So Mike's lecture, since we have some extra time. So again, the dimensions, time per cycle or time per revolution. We have the frequency. Frequency, we didn't say the units is Hertz is 1/second. So period and frequency, the frequencies is 1 over the period. And the period is 1 over the frequency. Okay, and you need to memorize that. So keep in mind, yes, the period is the opposite of the frequency. Okay, then angular frequency. So we saw before that omega is equal to 2 pi divided by t, because we just defined that t is 1/f, is also 2 pi multiplied by the frequency, and is measured in radians per second. The angular frequency or angular velocity. And then instead we have the tangential velocity v, which is 2 pi r divided by the period, or v is equal to omega r. So angular velocity multiplied by r. And the velocity vector always point tangent to the circle. So v remains constant in magnitude, but the direction continuously changes. Then we saw the radial acceleration or centripetal acceleration, v squared divided by r, or omega square r. where r is the radius, the distance from the center of rotation. And we see that is always perpendicular to the velocity and is always perpendicular towards the center of the circle. Okay, so this is our acceleration. Is also constant in magnitude, but also this change its direction every time, pointing at the center of the circle. Then we can have different components. And so the components at the velocity of the acceleration can be parallel to the velocity, and they can change the car speed. And while the component of the acceleration perpendicular to the velocity changes the car direction. So here, in case we have an acceleration, which is a composition of different accelerations. So the centripetal acceleration is the one going towards the center, but then you might have that the car accelerate. And so you have an additional acceleration along X. And so the final component, the final acceleration is going to be the sum of these two components, right? So this makes an example when you have multiple acceleration, not only the centripetal one, but also you have the car that is accelerating or decelerating, like in this case here. Okay, and then, okay, this is just repeating what is the centripetal force, which is the mass times the centripetal acceleration. Because the centripetal acceleration was v squared divided by r, is m v squared divided by r, or m omega squared divided by r. Then we spoke about apparent gravity, like when you have a centrifugal, a centrifugal acceleration and centrifugal force, it really makes an apparent gravity, an apparent weight of the object that is there. And that was pretty much the slides from Mike. So I hope that putting together the slides we saw today with all the problems and the one of Mike, I hope that, yeah, you will have a better understanding. So keep in mind that this is not going to be part of midterm 2. It's going to be part of midterm 3. Okay, are there any other questions that you want to point out here?
Also, some textbooks use the subscript CP or just C for centripetal. And our textbook, Young and Adams, uses rad for meaning the radial direction, but it's the same quantity. It's the centripetal acceleration that points in the radial direction toward the center of rotation. So it's the same thing, just you'll see both, you'll see all of those notations when you look in different, when you look at different resources. Yeah, so I'll post the Zoom and the slides in Laulima, the Zoom video in our YouTube channel. And yeah, have a wonderful long weekend. We all deserve a long weekend at this point. So if there are no further questions, I think. I'll just remind everyone that we have a lot of LA help hours today, right here at the Zoom address, starting basically at 10:30 today. So Julia, our LA, will be on duty, and then Evan follows her until 1:30 p.m. So do feel free to come back for help. Yeah. Okay. Goodbye. Bye-bye. Oh, it's not a dog in the picture. It's a little sheep, I think. Cool. Lamb, a goat. It's a lamb.
I'm like, oh, which type of dog is that? But
Well, Veronica, maybe I'll create a breakout room, and you and I could talk there for a second.
mhm.
Let's see, Carlos, before we do that, Carlos and Julia, are you two here?